Standard 10 Mathematics Part 2 Chapter Trigonometry, which deals in solving practice set problems in video number 18. So children, to move on with practice set problems in trigonometry, the problem on the board is somewhat different. For this, we'll have to recall theorem of equal ratios. What was this theorem of equal ratios? For what was it used? Definitely, it was used in ratio and proportion. What was ratio and proportion, children? It said that if A upon B is equal to C upon D, then A plus C upon B plus D is always equal to the basic ratios given, that is A upon B or C upon D. By using theorem of equal ratios. So, let's again recall, children. Given to you any ratio, A upon B is equal to C upon D, definitely by using theorem of equal ratios, which was applicable only for the operation of addition. It said that add all the numerators, divide them by adding all the denominators. That would definitely give you the original ratios, that is A upon B and C upon D. Thus, if A upon B is equal to C upon D, then A upon B is also equal to the sum of the numerators A plus C upon the sum of the denominators B plus D, which is also equal to the other ratios given in that respective problem. Same technique, the same basic theorem of equal ratios will be applied for this problem. Now, how do we do this? For this, again, let's recall our trigonometric identity, where we have the relation of tan with sec. Do we have such trigonometric identity which gives us the relation between tan and sec? Definitely, it is 1 plus tan square theta is equal to sec square theta. This is our trigonometric identity. So children, let's perform few operations on this trigonometric identity. We want only tan theta. So what can we do? Take plus 1 on the other side. So what are we left with? Tan square theta is equal to sec square theta. Plus 1 goes on the other side, gives us minus 1. Now over here on the left hand side, tan square theta resembles a square. A square can be written as a into a. Similarly, tan square theta can be written as tan theta multiplied by tan theta. What about the right hand side, children? Right hand side resembles the formula a squared minus b squared, which can be split up as a minus b into a plus b. A squared minus b squared can be written as a minus b into a plus b. That is sec square theta minus 1 square, that is 1, can be written as sec theta minus 1 into sec theta plus 1. So, let's move on further. Sec square theta minus 1 can be written as sec theta minus 1 into sec theta plus 1. Now children, to make this problem where we can apply theorem of equal ratios, we know that A into A or A into B, which is equal to C into D, can definitely be rewritten as A upon C, which is equal to D upon B, or A upon D can be written as C upon B, because finally when you cross multiply, you get the equation back. Same, let's apply it to this equation. Thus, we can have, as we want sec theta minus 1 in the denominator, let's take sec theta minus 1 towards our left hand side. So we are left with tan theta upon sec theta is performing multiplication when it goes on the other side. It will perform the operation of division, which is equal to, what is left on the right hand side? Sec theta plus 1 upon tan theta. Only one term tan theta is taken in the numerator, the other can be taken on the other side. Again, tan theta on the left hand side is performing multiplication. When it goes on the other side, division. So children, what have we reached to? We have reached to a step where now we can use theorem of equal ratios. A upon B is equal to C upon D. So we can use theorem of equal ratios as over here, A upon B is equal to C upon D. So therefore, by using theorem of equal ratios, we can say that A upon B, which is equal to C upon D, is also equal to A plus C upon B plus D. What is our A over here? Tan theta. What is our B over here? Sec theta minus 1. What is C? Sec theta plus 1. What is D? Tan theta. So finally, we can use theorem of equal ratios, which gives us tan theta upon sec theta minus 1, which is equal to sec theta plus 1 upon tan theta, which is equal to addition of both the numerators, that is A plus C. What is our A? Tan theta plus, what is our C? Sec theta plus 1 upon B plus D. Addition of both the denominators. What are the denominators? Sec theta minus 1 plus D. What is D? Tan theta. So this finally proves what is being asked in the problem, that we have to prove that if tan theta upon sec theta minus 1, you have to show is equal to tan theta plus sec theta plus 1 upon tan theta plus sec theta minus 1. So finally we have proved tan theta upon sec theta minus 1 is equal to, therefore tan theta upon sec theta minus 1 is equal to, only let's choose and write down whatever is asked, is equal to tan theta plus sec theta plus 1 upon sec theta minus 1 plus tan theta. So finally we have proved whatever is asked in the problem by using and recalling the basic, that is theorem of equal ratios. That given to you any ratios, definitely by using theorem of equal ratios, which is applicable only for addition, that if A upon B is equal to C upon D, then both the ratios are definitely equal to A plus C upon B plus D. Children, if you have some more ratios, like if A upon B is equal to C upon D is equal to E upon F, then definitely by using theorem of equal ratios, addition of all the numerators plus addition of all the denominators will definitely again give you equal to the original ratio given in that problem.
So children, remember this, the relation between the trigonometric ratios with their multiplicative inverse ratios according to the definitions of cosec, sec and cot ratios are 1 upon sine theta is equal to cosec theta. Thus we can say that sin theta into cosec theta is equal to 1. The second, 1 upon cos theta is equal to sec theta. Therefore, cos theta into sec theta is also equal to 1. And the third, 1 upon tan theta is equal to cot theta. Therefore, tan theta into cot theta is equal to 1. So children, the product of the trigonometric ratios with their multiplicative inverse ratios, the product is always equal to 1.